All right, activity 3.3, comparing probabilities using proportional reasoning. If you know the probability of an event, then you can use proportional reasoning to predict the number of times that event will occur throughout an experiment. Worked example. The probability that a spinner will land on the sun is 7 out of 20. If you spin the spinner 60 times, you can predict the number of times the spinner will land on the sun section. Step 1, set up a proportion. The number of times an event will occur over the number of possible outcomes. Then we're going to 60, so we set it up like that. Next, solve the proportion. As we've done with proportions before, we can cross multiply, so 7 times 60 should be equal to 20 times x. And then we have 420 equals 20 times x. We divide both sides by 20, and then x equals 21. And so, in this situation, if you spin the spinner 60 times, you can expect it to land on the sun 21 times. And so we can use proportions to make predictions with probabilities. So suppose these are the probabilities for the symbols on the spinner. So the smiley face, the sun, and the star. If you spin the spinner 40 times, predict the number of times the spinner would land on each symbol. So if the probability was 7 to 20, and we're seeing what would happen if we did 40 times, we're trying to figure out how many times it would land on the smiley face. So I could take 7 times 40, and that would be equal to 20 times x. When I solve that, I would get 280 equals 20 times x. Divide both sides by 20, and then I am going to get, let's see here, 14. And some of you could say that you could just scale those up and you would see the same answer, and that is correct to see. I'm just showing you what it looks like with proportions. For the sun, we were 2 to 5, and we're going 40 times. I do 2 times 40, set that equivalent to 5 times x. Then we'll have 80 equals 5 times x, and then x is going to be equal to, and divide by 5, and it'll be 16 times. Then, last but not least, there's 1 out of 4. I'm seeing what it would be to get to 40. I can cross multiply. 1 times 40 equals 4 times x, and x is going to equal 10 when all is said and done. Okay? B, if you spin the spinner 100 times. So it was 7 out of 20 equals over 100. It was 2 over 5 equals now over 100. And then it was 1 over 4, and that equals over 100. And I'm not going to cross multiply this time. I'm going to either scale up, so times 5 times 5, so it would be 35. Or think of percents. 2 out of 5 is the same as 40%, so this would be 40. Percents out of 100. And then this would be 25. Okay. C. How did you predict the number of times the spinner would land on each symbol for the given number of times the spinner would be spun? Scaled up. I used proportions. I used, because it's 100, I used what I know about percents. Do you think you would land on the symbol exactly the number of times you calculated in parts A and B if you spin the spinner? Why or why not? No. It is random, and I think it would be close to the prediction, but not exact. Okay. The actual number of times the spinner would land on a symbol is random. Okay. The prediction gives a close estimate of how many times you would expect the spinner to land on the symbol. So it's not giving me the exact answer, it's giving me a really good estimate. Okay. All right. To compare the theoretical and experimental probabilities, you can use a measure called percent error. In probability, the percent error describes how far off the experimental probability is from the theoretical probability as a percent ratio. Suppose you spun the smiley face 20 times out of 50 trials. The experimental probability of the smiley face is 20 out of 50, or reduced down to 2/5. The theoretical probability of the smiley face is 7 out of 20. They took this from the last page right here. And that's where I'm going to take these other ones from. Okay? Then, the percent error can be calculated using this formula. You take the experimental probability, you subtract the theoretical probability. Then you divide it by the theoretical probability. If I was writing this, I would almost want to consider putting parentheses around this because you do subtract that first. After you do that, you multiply it by 100 to get your probability. So let's take a look. They took the experimental probability, which was 2/5. They subtracted the theoretical probability, which was 7/20. They put it all over the theoretical probability, which is 7/20, and then they're going to times it by 100. So that's them setting up the problem according to the formula. Okay. In the second step, they made a common denominator of 20ths so they could subtract. Once they subtracted, they got 1/20 over 7/20. Okay. And so to do that, 1/20 over 7/20 is the same as 1/20 divided by 7/20. And that is the same as 1/20 times 20 over 7. And when I multiply that out, I get 1/7. And when you do that, 1/7 times 100 is going to equal about 14.3. And it's the about because this is a seventh, so the decimal goes on for a while after that. Okay? So they rounded basically to the 10th of a percent. Okay? Write a sentence to interpret the result in the worked example. The experimental probability is 14.3 is about 14.3% above the theoretical probability. Okay. Next, what would it mean to have a 0% error? Use an example with the formula to explain your reasoning. A 0% error would mean that the experimental and theoretical probabilities were the same. Okay. Use an example with the formula. Well, let's see here. So with the smiley face example, the theoretical probability was 7/20ths. So if we took 7/20ths as the experiment minus 7/20ths as the theoretical, and we divided it by 7/20ths, and then times it by 100, 7/20ths minus 7/20ths would be 0. 0 divided by 7/20ths would be 0. 0 times 100 would be 0. All right. Then 4. Use the spinner results. Use the spinner results from the previous activity to calculate the percent errors for the probability of the sun and the probability of the star and describe their meaning. Okay. And so that was, I used the data from when I actually ran the experiment, and then the theoretical probability was from the previous page. Okay. And so for the sun first, I would take my experimental probability of 10/50. I would subtract from the theoretical probability of 2/5. I would divide that by the theoretical probability of 2/5, and then I would times it by 100. Okay. For this one, I would then need a common denominator, and I see that I would use 50ths. So I would have 10/50ths minus times 10 times 10, 20/50ths over 20/50ths times 100. Then 10/50ths minus 20/50ths would be negative 10/50ths divided by 20/50ths times 100. Then if I think of this as a division problem, this as a division problem would be negative 10/50ths times, let's see, it would be divided by 20/50, but it'd be times 50/20. Reduce to 1, reduce to 2, and it would be negative 1/2 times 100. So it'd be negative 1/2 times 100. And then if I do that real quick, that would be negative, let's see here. Yeah, that would be minus 50%. And so for us, our experimental probability was 50% below the theoretical probability. Okay. If you think about this, we had 20% and it would normally be 40%. And so that's half of it. And that's negative 50%. Okay. Let's do the other example. Similar type situation. I would start by looking at my formula. So I would take the experimental probability. So I'd take 25/50. I would subtract the theoretical probability of 1 over 4. I would put it all over the theoretical probability of 1 over 4, and that whole thing would be times by 100. Okay? Then, if I'm looking for a common denominator here, I would use 100 as my common denominator. So I would have 50 over 100 times 25, minus 25 over 100, all over 25 over 100 times by 100. Okay? Then 50 over 100 minus 25 over 100 would be 25 over 100 divided by 25 over 100 times 100. 25 over 100 divided by 25 over 100 would be 1. So it would be 1 times 100. Or it would be 100%. And so for this example right here with the star, our experimental probability was 100% greater than the theoretical probability. Okay? And so I take the experimental probability, I subtract the theoretical probability, I divide that result by the theoretical probability, I times it by 100, and that is how I find the percent error in these probability situations. And so we will continue to work on and practice these, but this is definitely something you need to work on and try to know. This is like the super tough thing in this section so far, at least in my eyes.